You ever wonder why some dental fillings seem to last forever and others just don't? Well, it's not always about how you chew. A lot of it comes down to some really cool chemistry. Today, we're going to dig into a simple but revolutionary change that completely transformed dental fillings, the jump from low copper to high copper amalgams.
So, here's what we've got on tap. We're going to start by uncovering amalgam's one fatal flaw. Then, we'll meet the hero element that changed the entire game. After that, we'll check out the modern options dentists have, cover the golden rules for making them last, and wrap it all up with a quick study guide and a look at what might be next.
All right, Section 1, Amalgam's Fatal Flaw. You know, to really get why modern fillings are so tough, we have to go back in time and look at the problem they were designed to fix. So what was the secret weakness lurking inside those old-school amalgams?
So what was the deal? Why did these early fillings have such a bad reputation for failing? Well, the answer isn't about technique, it's about the chemistry happening inside the filling itself. Turns out there was a single, very problematic component.
And this is it. This is the villain of our story, the gamma-2 phase. Think of it like a chemical traitor inside the filling. In those old, low-copper amalgams, tin and mercury would get together and form this compound, and it was just incredibly weak and loved to corrode. It was like building a brick wall with mortar that dissolves in the rain. The whole thing would just break down from the inside out.
So, Section 2, Copper, the game changer. How in the world did dental science take down this villain? Well, the solution was actually pretty simple, but wow, it completely rewrote the rulebook for amalgam chemistry.
And the magic number that started this whole revolution? 12%. Once researchers pushed the copper content above this threshold, they created a whole new class of high copper amalgams. And this wasn't just a tiny tweak, it was an absolute game changer for dentistry.
This is where the chemistry gets really elegant. You see, in the old formula, tin would bond with mercury, and boom, you've got that weak gamma-2 phase. But in high copper amalgam, copper acts like a bodyguard. It has a way stronger attraction to tin, so it swoops in and bonds with it first. It basically stops tin and mercury from ever getting together. No gamma-2, no corrosion. Problem solved.
And the real-world result of this simple chemical switch? It's huge. By getting rid of that gamma-2 phase, the lifespan of these fillings just skyrocketed. Restorations that used to fail pretty quickly now give patients solid performance for over 12 years.
Okay, Section 3, Admixed versus Spherical. Getting rid of that weak link was the first giant leap. But even within the world of high copper amalgams, dentists have choices, and those choices are based on the actual shape of the metal particles. It really affects how the material handles.
The two main types you'll hear about are admixed and spherical, and really the biggest difference comes down to the shape of the alloy particles. That shape completely changes how much force a dentist needs to use to pack or condense the filling into the tooth.
So, admixed amalgams are made of these irregular, kind of jagged particles. This mix makes the material feel stiffer, so it takes more pressure to pack it in. Now, you might think more work is a bad thing, but a lot of dentists actually prefer it. That extra pressure is fantastic for pushing against the little metal wall they use during the procedure, and that helps create a really nice, tight contact point between the teeth.
Then you've got spherical amalgams. These have tiny, perfectly round particles. Imagine trying to pack a box with jagged rocks versus packing it with ball bearings. The ball bearings just flow right into place, and that's exactly how spherical amalgam feels. It needs a lot less pressure. Plus, it has this huge advantage. It gets super strong super fast. This high early strength makes it the perfect choice for really big fillings.
All right, Section 4, Designing for Strength. Of course, the material itself is only half the battle. To stop it from fracturing, you have to use amalgam the right way. There are some very specific rules of engagement.
You know, to really understand how to use amalgam, you have to get its personality. Think of it like a ceramic plate. You can stand on it and it'll hold your weight. That's amazing compressive strength. But if you try to bend it, even a little, snap. That low tensile strength is exactly what makes amalgam brittle.
So, to work around this brittleness, there are two design rules that are absolutely non-negotiable. First, the filling has to have enough bulk. It needs to be at least 1.5 to 2 millimeters thick anywhere you're going to be chewing on it. Any thinner, and it's likely to fracture. Second, the edge where the amalgam meets the tooth, that has to be a sharp 90-degree angle. Any thin, feathery edge will just chip right off.
Section 5, the exam review. Okay, let's pull all this together. If you're studying for an exam, or you just want the absolute key takeaways, this right here is your ultimate cheat sheet.
This is it, the core comparison. If you remember anything from this, remember this slide. The big problem with low copper? The corrosive gamma-2 phase. The solution? With high copper? Getting rid of it completely. The magic number for copper content? 12%. And the result? A lifespan that went from failing fast to lasting well over a decade.
So how does amalgam's risk of fracture stack up against those modern, tooth-colored composites? Well, the key thing to remember is amalgam is brittle. If those design rules for bulk and 90-degree edges aren't followed, it can fracture. Interestingly, while composites are less brittle, amalgam actually has an advantage. It expands and contracts with temperature changes almost exactly like a natural tooth, which helps it keep a better seal over time.
And that brings us to Section 6, the quest for alternatives. Because for all of its strengths, there's the elephant in the room. Amalgam contains mercury, and that has driven a decades-long search to find the perfect mercury-free alternative. So, what's on the horizon?
Well, these are the main avenues researchers have been exploring. They've been experimenting with creating new alloys using metals like gallium and indium. The big hope is that these materials can mimic all the useful properties of mercury without the same concerns.
But, and this is a really important but, we have to be realistic about where things stand right now. This quote really sums it up perfectly. While these alternatives are promising, as of today, none of them have managed to match the all-around strength, durability, and sheer longevity of high copper amalgam. The quest continues.
So, from the fatal flaw of that gamma-2 phase to the elegant chemical solution of high copper alloys, the story of amalgam is just a perfect example of how material science is always pushing forward. Understanding these fundamentals is so key. To stay updated with more insights just like this one, be sure to follow Dr. Sarang Suresh.